I want to look at Descartes' rule of signs. And anytime you do something with René Descartes' name on it, you should get a little bit excited. He was one of our most impactful mathematicians in history. So this is kind of exciting. And what I'm going to do is I'm going to show an example of something first, and then I'll explain what René Descartes' rule of signs is and how it's useful. Alright, so first let's take this example, this polynomial. We have 2x cubed plus 3x squared minus 14x minus 21. And I want to point out something right here. Notice when I go from 3x squared to negative 4x, there's a change from positive to negative. Right, so we have one change from when it goes from positive to negative. Notice that's the only time, because first we had positive, positive, and then we have negative, negative. The only time that the signs change is right there in the middle. Okay, so we have one sign change. Now that's important. Okay, so let's try this again. This time I'm going to plug in negative x. So I have 2, that means negative x cubed plus 3 negative x squared minus 14 times negative x minus 21. And to simplify that, remember when I multiply a negative by itself an odd number of times, it becomes negative. So here I get negative x cubed plus 3x squared, right? Negative x times negative x is positive x. I get a plus 14x here and a negative 21. Now I want to look at those sign changes. Look, I went from negative to positive, there's one. Positive to positive, that's not a change, and then positive to negative, so there's another one. So actually in this example, I had 2 instances where I have some sort of sign change. Okay, now these changes in signs are what we call variation in signs. So the polynomial f of x, when I just plugged x into this function, I had one variation in sign. I'm going to call that k1. So here k1 was 1. And when I plugged in negative x into the function, I got 2 variations in signs. I'm going to call that number k2. So I had 2 variations in signs for f of negative x. Okay. Now why is that useful? Because here's René Descartes' rule of signs, and some books word it a little bit differently, but this is how I'm wording it, okay? So we're going to let f of x have k1 variation in signs, and we're going to let f of negative x have k2 variation in signs, just like we did with this example. Now here's what that means. 1, that means that there are k1 or k1 minus 2 or k1 minus 4 or k1 minus some sort of even number positive real roots in this polynomial. So the variation in signs of f of x tells you something about the number of positive real roots possible for this function. And secondly, there are k2 or k2 minus 2 or k2 minus 4 or k2 minus some sort of odd number negative real roots. So f of negative x, the number of variations in signs in f of negative x, tells you something about the number of negative real roots that we can have. Alright, so now going back to this example then, we saw that k1 was 1. So how many positive real roots can I have? We can see that this function is going to have one positive real root because k1 equals 1. And I can't have, if I do minus 2, I'm in the negatives. Okay, so that's not going to work. So there is going to be one positive real root. What about negative real roots? And then this function will either have 2 or 0 negative real roots. How do I know that? Because k sub 2 was 2. And so I could subtract 2 and get 0. And below that I'm going to be negative. So I'm either going to have 2 or 0 real roots. Okay, so that's kind of the tricky part you have to keep in mind, is that once you find your k1 and your k2 values, you just keep subtracting 2 until you get to the negatives, and that'll tell you the candidates for the number of real positive and negative real roots that you can have. Alright, so let me show you an example, and we're actually going to find the real roots for this example. Okay, so we want to find the real roots of g of x, which is x to the 4th minus 7x cubed plus 5x squared plus 31x minus 30. So it's a 4th degree polynomial. We're going to find our k1 value by counting the variations in our sign. So let's see, I went positive, negative, positive, positive, negative. Alright, now notice, there's a variation in sign, went from positive to negative. There's another variation in sign, and then over here I went from positive to negative again. So that means that my k1 value, what we called k1, is going to be 3 or 3 minus 2, which is 1, or Well, that's all. Okay, it's either going to be 3 or 1. All right, now let's try to figure out what's going to happen in g of negative x. So when I plug in a negative, remember the even powers are going to stay the same. So I have x to the fourth, but my odd powers are going to flip signs because negative x cubed is negative x quantity cubed. All right, so there we have it. And we have plus 5x squared minus 31x plus 30. Now, if I look at my variations in sign here, let's see, I want positive, 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 nothing so far. Oh, there's a negative and there's a positive. Okay, so that means I have 1, 2. That means my k2 value is either going to be 2 or 0 negative real roots. Okay, now how do I figure out what these are? So this is where we use rational root theorem again. And so if you remember, the rational root theorem says if I have a rational root pq, the numerator is going to divide the constant term of my polynomial. So the numerator is going to divide 30. That's a lot of option there. We have plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. Okay, your q will have to divide your leading coefficient, which is 1. So the only thing that these could be divided by are plus and negative 1. Why don't we try 1 first? And again, to do that, you say 1, negative 7, 5, 31, negative 30. Hopefully we get a 0 here at the end. Hopefully that's a 0. Let's see. So you bring down the 1. 1 times 1 is 1. You add to get negative 6. Negative 6 times 1 is negative 6. So you add to get negative 1. Negative 1 times 1 is negative 1. You add to get 30, which is looking good for us because 30 times 1 is 30. And then we add those together, you get 0. Okay, now I went through that really quickly. I have a video covering the rational root theorem and synthetic division if you need to go back and look those up. All right, but here we have it. So 1 is a root. That means that this thing now can be factored as x minus 1 times x cubed minus 6x squared minus x plus 30, like that. Okay, and we found a real positive root. So we know we at least found 1. There could be 2 more. Okay, so we're going to try to find some more zeros, but now that we've already found 1, I don't have to divide all of this. I can just divide the cubic part. Okay, all right, so let's try negative 1 and see how that goes. So I'm going to divide 1x cubed minus 6x squared minus 1 plus 30. Okay, bring down the 1, and I say 1 times negative 1 is negative 1, and then we add negative 6 to get negative 7. Times negative 1 gives me 7, plus a negative 1 gives me 6. 6 times negative 1 is a negative 6, and I'm not going to get 0 there. So negative 1 is not an option, and we've already taken care of positive 1. All right, so let's move down the chain. Let's try, how about negative 2? So we're going to set this up again. And the great thing about synthetic division is it's so fast. Once you see it, it's really quick. So we bring down 1. 1 times negative 2 is negative 2. Then we get negative 8. Negative 8 times negative 2 is a 16. So that gives me a positive 15. Times negative 2, look at that. Negative 30. I get a 0 as a remainder. Great. So I found another 0 here. This means that g of x can be written as x minus 1, x minus a negative 2, which is a plus 2, times x squared minus 8x plus 15. Okay, and since that's a quadratic, I can factor that. I get x minus 1, x plus 2, and then two things that multiply to give me 15, add to give me negative 8. How about minus 5 and minus 3? And so there it is. G of x is completely factored. And now also notice the real number of positive roots, positive real roots, was 3 because we had 1, 3, and 5. And the negatives was negative 2, 1, just like we said with Descartes' rule of signs. Okay, now we actually combined multiple topics here. We did Descartes' rule of signs to figure out the number of positive and negative real roots. We used the rational root theorem to figure out a candidate list of what those could be. And then we used synthetic division to test those to see which ones were actually their true real roots. And it was allowing us then to factor g of x into something that is really easy to visualize, but it would have been hard to do without these techniques. I hope this makes sense. If you have any questions on how to use this, I'd be glad to help, and thank you for watching.